Welcome all to the MateriAlZ seminar. Today we have Dr. Kaitlyn Crawford from University of Central Florida. It's a great pleasure to have her here. Dr. Crawford got her PhD from University of Maryland, College Park, and then moved to Illinois and then Northwestern with John Rogers Group, where, of course, she's done lots of wonderful things. She's going to her talk today is on sustainability in human health monitoring, and we're looking forward to getting educated on that. Thanks, Kate. Feel free to use this.
Thank you. Thank you very much. And just to do one more sound check, you guys can hear me online, okay?
Yes, we can.
All right. Just going to maybe if I can hide this before we get started. Who can find it first? It says float, hide, video panel. Yes.
Sorry.
No, that's not the video panel. One more time.
On the back, height, floating, between control.
Thank you. Yes, that's it. There we go. Okay, let's do this. Right. Good morning, and thank you for being here today, or thank you for the opportunity to be here today. And I'm excited to share with you guys some of my story with you over the next several minutes. I am going to click back on the presentation now. Yes. Okay. The motivation for our research stems from living healthier, flexible electronics, and then doing these both sustainably. So this is the theme for the story that I'm going to talk to you about today. And a little outline to give you some guidance of how this is going to work is I'm going to talk about these topics in general, but I'm going to do it through two different examples of health monitoring devices. And then I'm going to switch gears about 2/3 of the way through the talk and shift to transient electronic devices. These are ones that are biodegradable. And then at the very end, I'm going to introduce some preliminary work that we're doing in the direction of transient electronics, and then wrap up with some comments about societal impact in graduate research. I like to start with this because we are having a longer life expectancy, and Hong Kong and Japan lead the world with a life expectancy of 85. We're a little bit trailing behind, around 79 here in the United States, but this looks, very unique. This is Johanna from Germany. She's 86. Well, she's in her 90s now and still active, but 86 doing gymnastics. And while this looks like an anomaly or a very rare thing, it's actually becoming quite common. In the second half of our lives, we are now living not just longer, but we're also beginning to live healthier too. And one of the things that I'll point out here as well is that we're wearing new accessories. We have devices that allow us to measure things like our heart rate and our blood oxygen concentration, for example. And so when we think about living healthier for longer, we're also having new technologies that allow us to be able to monitor physiological and biological markers, within ourselves, so that we can look at things like blood oxygen, breathing, our sleep, our activity, our glucose, whatever kind of device you can imagine. We can make it, and we can accessorize ourselves and decorate us in all different ways. And so the thing is, though, that when we're doing this, we can use these wearable health monitoring tools to prevent, diagnose, maintain, and even enhance some of our capabilities. And this is one of the reasons why that can help us to live healthier for a longer period of time. One thing, though, is that there's an inherent mechanical mismatch. So I'll take smartwatches for an example. They're nice and they give us useful information about heart rate, for example, but at the end of the day, there's still a rigid brick of silicon with integrated circuits, and it's brittle, and the modulus is very high. And we literally take this rigid thing and we strap it to ourselves with a silicone, watch wristband, but it's not really conformal, and it certainly does not match the textured and soft curvilinear nature of our skin, or the modulus for that matter, which is quite a bit lower. And so one of the things we are interested in doing is how do we get these electronics to a way that it fits our textured skin and curvilinear skin more easily. This work mathematically has been worked out by others, so this is not mine, but it's a nice example that shows if you can make a device thin enough, then the van der Waals interactions can take over, and you can begin to have this intermolecular interaction between a very thin device and the surface of the skin, so you have more intimate contact. And so in that case, you would have more sensitivity, and you should be able to have greater accuracy with the better interaction there. So that's the question: is can we take this map, this theoretical, and can we make an action?
उधर की चाबी किसके पास है?
I think there's a microphone that might need to be muted. Can you check your Zoom to make sure everyone has their microphones muted, please? Thank you. Right, so we want to be able to see if we can make a device like this that is ultra thin and conformal for different types of electronic and health sensing. This is one example of an optical tomography, where the top example is the palm of the skin, and the outermost bright color is the stratium corneum, the outermost layer of our skin. And the bottom image is of a device that's laminated onto the surface of the palm of the skin. So you can see that when you actually do make these electronic devices much, much thinner, then the formal contact becomes much better. Now, it's not perfect, of course. If you look closely, you can see there's some delamination here and also over here, but it's a step in the right direction for having the more better mechanical matching for our devices. This is a switch though, so then if we're thinking we can make so many different devices, what exactly should we make, right? The life expectancy is very long. Go ahead, come on over here, have a seat. You sit right over here or over here, plenty of space. Come on over. So I wanted to look at what are some of the reasons why we do expire. Like we're living longer, but we're not living forever. Why is that? So in the United States, the #1 cause of morbidity is heart disease. And the second cause of morbidity is cancer. So I'll come back to heart disease in a few minutes, but I'm just going to focus on cancer for a few minutes. I'm not a cancer researcher, but just the idea of it. And if we look at the different types of cancer, actually in the United States and in some other countries as well, skin cancer is the #1 type of cancer that humans are diagnosed with, at least in the US. This translates to 1 in 5 Americans are likely to be diagnosed with skin cancer at some point in their life. That's 9,500 people every single day getting some sort of skin cancer diagnosis. And we know that sun exposure plays a big role in that. So there's a nice sunshine there. So would it be possible to do some sort of UV monitoring? How much exposure to the sun are we getting every day? And can we do this with epidermal electronics or some sort of visual design that we can wear that would tell us if we're getting too much sun exposure? One example I'm going to show you is, in this case, instead of using electronics, we're using a colorimetric method of epidermal device. And we want to visualize the sun exposure using this colorimetric method. And in this case, we take 2 different chromophores. So we have a crystal violet lactone and we have a Congo red. And the CVL goes from a colorless at a higher pH to this darker purple bluish color at a lower pH. And Congo red starts out red, but when you're at a lower pH, it turns to a blue color. So if we could figure out a way to correlate sun exposure with pH value, then we might be able to see color differences and then see how much sun exposure we've had. And we can exactly do this with something called a photoacid generator. If we can composite the chromophore together with the photoacid generator, then as it's being exposed to light or the energy from the sun, then it breaks down, causes a lower pH, and you should be able to see these color changes. So we did this on the bench scale in a more quantitative way, although overall colorimetrically, of course, it's qualitative. But you can see in the CVL composite, then it starts out relatively colorless and then turns to darker blue colors as you increase the amount of energy exposure. And you could do the same thing for the Congo red, where it starts out a red and moves to a much, much darker color. And so if we then make these into composite with polymers and laminate them in very thin, film structures, then we might be able to have something like this UV dosimeter that you could actually wear with you. And as it changes colors, we can see, okay, it's been time to put more sunscreen on, or it's time to get out of the sun because it's at this color, it's time to move. So about these wings, so we use the butterfly wing. And on the left is actually a temperature chromophore, so it's a thermochromic, and it just changes colors when it's hot outside, so that's like a nice wing. On the right is that Congo red, and on the bottom is the CBL. And we separated that out because actually my primary contribution to this is to develop the different films, so you can have UVA pass through and not UVB, or UVB pass through and not UVA. So we can see the difference in UVA versus the UVB exposure. And then the circles in the center are the color control, because then we would integrate this with some electronics. By the way, the back here is an NFC coil, near field communication. And this is transmitting the temperature of the skin over to an app. And this is something that you might, yeah, come on over here. There's space for you. Yeah, have a seat. Welcome. Yep, this is happens when you're a little bit late. So you might notice a name here. This is Professor Butra in the BME department here, and he worked on the hardware electronic development for this project. And we use this color control in the center as an RGB color wheel, so that if you're in different lighting, we can control and we know what color it should be, and we can calibrate. We can calibrate for that. And of course, we can also read what is the skin's temperature. But here's the thing. Maybe you forgot to wear this UV dosimeter for the day, or maybe you forgot to put sunscreen on, and you're like me. If you're outside for 5 minutes, you will definitely get a sunburn, like hands down, especially here and in Florida where I live. So we want to think about what are other ways that we can evaluate skin damage. So, okay, I forget my animations. So we wanted to check the modulus, right? This modulus of skin, you can look it up or take my word for it. It's around 0.4 to 0.5 megapascal modulus. And we measured the modulus of each of the individual layers, and they fall within the similar modulus of the skin. So that's just good to confirm, right? It could be flexible, but maybe it's very rigid, and that's not a good mechanical matching. Right, so here's the sunburn anyway. So you already stayed outside for too long. Yes, it's a little painful. If you guys have ever had a sunburn, what do you do after you have a sunburn, and what happens to the skin after you have a sunburn? And that's a question that we were curious to answer. And in this case, we look at the skin. We have the stratium corneum and the epidermis, the dermis, the subcutaneous fat, etc., the sweat glands, and the capillaries. Now, putting our engineering hat on, when I see sweat glands and capillaries, I think about heat exchangers. And when I think about heat exchangers, then I start thinking about thermal conductivity. And so I've listed a box here of standard thermal conductivities of water, 0.6, of blood is a little bit lower, 0.5 watts per meter Kelvin. Then you have muscle, it's a little bit lower, and skin is between 0.2 and 0.32 watts per meter Kelvin. And so if we could figure out a way to measure thermal conductivity of skin, and we see that the skin is different than the blood, then we might be able to see some differences on how radiation burns heal and how that affects the skin over, thinking into the future, what that might look over time if we wanted to measure that. Right now in the medical field, the way that we look at this is through medical IR imaging. This is fantastic because it has really high resolution. You can look at blood flow as well as the different temperature and components of the skin. But despite the fact that it has really good high resolution and spatial temporal mapping, it's cumbersome, it's expensive, there are problems with space. So to get the image on the last of an arm on the last slide, we really have to basically strap the person down and put markers on their arm. And the IR camera is not very good for curved surfaces, which is not matching the curvilinear nature of our skin. There are still some chairs over here if you want to come all the way in here. Come on over. Yeah, at least we have at least 4 more. You can sit at the front too if you'd like. Yeah. Welcome. This doesn't need to be Great. So now that's how the medical industry does it. Could we figure out a way to do the similar sort of very ultra thin device and incorporate that in and look at UV radiation burns? Of course, we don't want to reinvent the wheel. As students, it's really important to remember that so many things have already been invented. And so instead of reinventing the wheel, see how other people do it. So in industry, they measure thermal conductivity in various methods, but one method is the hot disk method. This is where you take a wire and you run a current through it, goes into the resistor, and of course the resistor is going to heat up. And most metals, at least in the biological temperature range where it's relevant, is going to be linear with temperature. So if you increase the temperature, then you increase the resistance, and then increase the temperature, your resistance also increases, and this should be in a linear fashion. And so that's how they measure it. And then they can calculate thermal conductivity using the transient flame source model. It's a very standard technique. So the plot on the right is what we're most interested in. It's a change in temperature as a function of time. So not just what is the temperature, but the change in temperature. Because then if you take a slope of this line and you can solve the thermodynamic heat equation to extract out what is the thermal conductivity. So we use an analytical method to do this, but we could measure it from the slope. And the difference between the red and the black and the blue lines is to show the reproducibility. You could get the similar thermal conductivity value from measuring 2 seconds or 20 seconds or 40 seconds. We get very similar values, and that the measurement from one device to another is similar. This is the line is thickness is thicker than the error bar's size was. All right, well, can we take this from industry? That's what we wanted to do and translate it to this ultra thin device that I've been talking about. And this is an example of a device that I worked on, and we use the serpentine coils, so that allows some degree of stretchability. Metals are not stretchable, but if you give some architectural difference, then we can have some stretching. And then we put a coil, a labyrinth coil for the resistor component. And you can see from this image that I snaked it through some glass pipette tips. So they're like little glass rods. So you can see that it can be concave or convex, and that should laminate very well to the skin. And you can't see this in the image because it's transparent, but it's laminated on a very thin, transparent, silicone substrate. And so that would stick to the skin very nicely just through van der Waals interactions. No other adhesive is there. So the next slide I'm going to show you, and it's going to be a fast forward through over a year's worth of work. So all that hard toil that you do in the graduate, lab and your graduate studies, I'm fast forwarding through some of that. And before we could put it on skin, we had to prove, does it actually measure thermal conductivity? We have to measure it on known surfaces, where we purchase standard materials that have very well characterized thermal conductivity, and then measure that. And then we do synthetic skins in different layers. We do high thermal conductivity, low thermal conductivity. How deep does it measure? How far out does it measure? So we had to do all of this background stuff before we could actually put it on skin, and that to then sunburn the skin as well. So we wanted to be really sure about our device. And in fact, not only did we use the analytical method, but my colleague and I developed a scaling law. So we could simply put in what the estimated diffusivity is, and some of the other parameters about the device size, and we can extract out just very simply an approximated effective thermal conductivity. So the images that you see is one is a right volar forearm. That means the inside of the forearm before a burn occurs. And then the next image is 5 hours after the burn has occurred. And then you can see it gradually healing over time. When you measure the device in the same spot from each time, first, I want you to focus on the black line of this graph at the top. This is before the sunburn. And you would expect a higher change in temperature for the before, because if you remember, the skin has a much lower thermal conductivity, which means it's not dissipating heat as effectively. So it's accumulating, you expect to see a higher delta T. But then if you look at the next line as the red line, then you have a much lower change in temperature. And that's because we have more blood near the surface of the skin. So blood has a higher thermal conductivity. It's more effective at dissipating heat. And then 2, we have mass transport of heat right from blood flow away from the system. And so we can measure the effective, not an exact, but effective thermal conductivity value, taking those differences into consideration. This bar graph on the right is the same thing from the plot, but it's taken at the 60-second marks and then transposed into a bar chart. is when we're collaborating with the clinicians, despite our year to year and a half of very hard work of figuring out that this thermal conductivity is 0.46 watts per meter Kelvin or 0.57 watts per meter Kelvin, the clinicians were really just interested in seeing this visual change of how the sunburn is healing as a function of time. And one of my favorite parts about this plot is that we can see the black line at the top. The black line is the skin's temperature. I just found this was interesting because as a person who has been sunburned before, you feel the skin and it feels hot to the touch. But of course it does. You have more blood in the surface of the skin and you've disrupted the thermal, regulation there, but your skin's temperature was really maintaining about the same from day to day, even though your skin might be feeling more hot. You could imagine then, of course, using this in a wide range of different applications. So one example would be measuring the blood flow. You can actually measure the velocity of blood flow by doing an array of sensors around a near surface vein. And if you are sensing if you're sensing one and running current through another and let the other ones just read the resistance, you can actually calculate blood velocity. Then we could integrate this with impedance sensors. So we have a regular resistor, and then we have impedance, and you're looking at hydration and thermal mapping at the same time over an array of space. This is a 16 array device where we do thermal mapping. You could also look at things like nail health. And then of course there's the more, quantitative, like not more quantitative, but there's the back end part, like how deep does it measure? How wide is it? How much power should we add? What's the size of the device that's the best? And we can look at that as well. So there's just a lot of applications, like I said, that you could look at. I'm going to prepare to move forward and talk about the next set of devices. But erythema and CRPS, complex regional pain syndrome, that's what CRPS is. Raynaud's abnormalities. If you have an abnormal marking on the skin, it's likely to have a different density. So that means it's probably going to conduct heat differently. So you might be able to do some measurement in this way, wounds, maybe looking at diabetic ulcers, etc. Something to think about. I'm going to just finish talking about this device with one example. And so this example is measuring heat stress. And I'm using firefighters for this example, is that this is just a hypothesis of what something that we could potentially do, is that one, we know one of the leading causes of death of firefighters, aside from cancer, which is by and large the largest, but the on-duty firefighter deaths are due to sudden cardiac events. And that's where this heart disease I mentioned earlier comes back into play. And we know that firefighters are often exposed to high levels of heat stress. And that we know that heat stress also causes cardiovascular strain. That's like a well-known understanding. But something that we don't know is if a firefighter or anybody is continuously exposed to heat stress, like strenuous heat stress for long periods of time, day in and day out over the course of a career, is this something that can contribute to things like sudden cardiac events that we see so common in firefighter deaths? And that's a really important question to ask. And so one of the preliminary data, not on firefighters, but with the device in general, is if we could start to measure or see differences in heat stress, or at least when the body is experiencing heat stress. So the idea is that if we could develop a device that could monitor within the person, so it's relative, to each person, or, it's different for each person. But then in that case, we could at least track your own heat stress exposure, and you can see how much heat stress you were exposed to on a given day. And then if you could think about this over a cohort study over a very long time, then you could have that data available to call back on and say, okay, this is maybe a contributor to something. And we don't know the answer to that yet. So until we develop a device, maybe something that looks like this one, then those studies can't be done. And so one of these proposals is something that I have pending right now. I'm really looking forward to a positive email in the next 5 days. So I'm very anxious about this. But this is also something that involves Jeff Burgess, which is here at University of Arizona. He's a medical doctor and a leader in the area of cancer research and for firefighters. So he provided a letter of support for this proposal. I look forward to the opportunity to work on it. And so I wanted to share that with you guys. Okay, that's it for those device examples, the UV dosimeter and the thermal properties. So now I'm going to start looking at this as a big picture. So where do we go from here? What other kinds of things can we do? Because I have experience in collaborating with projects that are related to sweat sensing and looking at different biomarkers in sweat or salt concentrations. I've had experience in looking at different optogenetic implantable devices and doing studies related to pain or bladder function. That's what those examples are. I've worked in flexible electronics with piezoelectrics, and also again with different types of thermal sensing from different modalities. It's like a 4 electrode instead of a 2 electrode sensor. So this is exciting because it's a modern technology, right? We're a modern society, we're living longer, we're living healthier. But the thing is we're really just decorating ourselves with electronics. And on the one hand, that's great, but on the other hand, it's causing a really big problem. One of the problems that it's causing is electronic waste. This is a significant issue. We all already have drawers of old cell phones or laptops, but where do those go? And as we begin to wear things like smart rings and smart shoes and smart headbands, eventually new technology is going to come along. And what are we going to do with all these wearable health monitoring electronics that were meant to help improve our lives, but yet it's going to be reducing our quality of living? So in 2020, approximately 50 million metric tons of electronic waste was generated, and about 80% of that ends up in these landfills. So if we could develop resorbable electronics that would achieve some of the same things, or that could be recycled, but today I'm focusing on resorbable. We could have a discussion about recycling later. We might be able to reduce the impact of some of this electronic waste while maintaining this modern, push to do human health monitoring. Of course, I'm not the first person to think this, right? This has been an area of under research for some time. So I put one of the earlier examples up here, as well as some of the more recent examples. And it's a few that I've listed here of many examples, just to give an idea that there are people researching using bio-derived materials. We're looking at energy storage, capacitors, piezoelectrics, transistors, electrodes, etc. And in fact, if you're interested in this area, I've also compiled some recent reviews written by some really fantastic individuals. So you can read about those. Are all new reviews. And then the examples in transit electronics that I've been affiliated with are the pictures on the bottom. And today I'm going to just talk about one full example, which is the one on the left with that NFC coil, and then show you one slide of preliminary data related to a piezoelectric device using a natural material, mostly natural material as well. So this is where we're going to go next. The reason why I want to talk about this particular example is that it's easy to replace this coil, let's say, with magnesium instead of with gold, right? That's the gold is standard. And there's inherently issues with using magnesium that will need to be worked out as well. But the problem is really the encapsulation material. Because if you are using a polymer that's soft and flexible, then the permeability, the diffusion of that through the film is going to be much higher. And then you have a device that takes maybe a year to degrade, but it stops working within a day because of the water vapor, transmission or the water absorption. And so we want to focus on how to make better encapsulants that are also biodegradable, but can, perform for longer periods of time. And so to start this, we very simply wanted to look at naturally occurring, non-toxic, edible, low-cost, readily available materials. So we came up with candelilla plants, soybeans, and the myrtle shrub. These are waxes. And naturally, we know, of course, these waxes should be hydrophobic, and we measured that with the goniometry. And indeed, they have similar hydrophobicity, the similar water contact angles, and that doesn't really help us out very much. We want to know which of these is better, or maybe they're all the same. We don't know yet. So we decided to make pucks of these wax materials and put them in water and see how much water they absorb. But also at 22 degrees, that didn't really give us much information either. None of them really absorbed very much water. So we thought, well, eventually we'd want to use this maybe for an implantable electronic. So let's increase the temperature to body temperature at 37. And then finally, we actually started to see some difference. And the soy wax absorbs a significant amount of water at body temperature. And the myrtle, absorbs some water, but the candelilla still stays pretty low. And so that might be our winning candidate to pursue. So we looked at two other things then for the candelilla wax, and then we included the soy here too, just so you can see that. We made these squares of magnesium film by a deposition method. And then we coated each of those with like thin layers of the wax. And we waited to see how long it takes for the water to diffuse through and cause the resorption of the magnesium. So you can see the color starts to change around 7 days. And then we connected 2 wires to this so we could also measure the resistance, because as the magnesium is being resorbed, then you have an increase in resistance, which you would expect to see. And what's nice is that when you're looking at the change in resistance compared to its original resistance, that the candelilla starts to increase around like 8 days, 7 days, which matches really conveniently, very nicely with the visual image, where it starts changing color around 7 days. And then, by 13, the resistance is just shooting up really high. We did another thing is looking at the time to doubling of the resistance. And then we did an analytical model of what this should look like. And then we estimated from that what the diffusion coefficient should be. And so we determined through estimating that the diffusion coefficient should be somewhere around 6 times 10 to the minus 15 meters squared per second. And then as a comparison, to give you some frame of reference, PLA, polylactic acid, is a very common encapsulation material for transient devices. That is about 10 to the minus 13 meters squared per second. So it's a really good barrier material. We're going to see if we can use it in some of our transient devices. So as a proof of concept, we used PLGA, the polylactic glycolic acid, and we used a magnesium coil, and we used a conductive solder using the paste, actually. So we used the wax and made a paste and made it of conductive material. So the only thing that's really not resorbable or biodegradable is the LED that we put on here for demonstration purposes. And then we encapsulated that with our candelilla. And then what we next did was we implanted it into an animal model. And so I'm warning you because I'm going to show you what that looks like after we implanted it. We did this in a small animal model for 3 days. It was awake, freely moving rat that seemed to not realize that there was a device there. This is important for areas of like optogenetics. If you have questions about that, we can talk about it afterward and what some of the significance of optogenetics is. But after 3 days, there's a problem. Wax is a brittle material. So while it's really good at a water vapor barrier, it's not very flexible. So we can make it very thin, but then, these guys move. So the device is cracking and then it starts to short and not work. But we also wanted to see, well, can it resorb over time? So we had an IRB approval also to look at small centimeter squared pieces to look at over the course of time, how do these resorb? So we found that after 3 months, the thickness of these decreased by about 30 microns on average. And so the body does resorb. And I did not put the histology here. We can talk about that if you'd like to, but we used controls and there is no like inflammation activation in the space. It looked just like a normal, just like a normal control, the positive or the negative control. That's the next question, right? And material science and engineering, we want to use materials, but we want to do the structure property relationship. Yeah. So we wanted to know what exactly the structures, what makes this a good encapsulant. So we ran GCMS, gas chromatography, mass spectroscopy, and we found in candelilla, it has a very high concentration of hydrocarbons and some concentration of aromatic resins. And the myrtle wax doesn't really have much of either of those. And then I'm not showing the one for soy because it didn't work out so well on our instrument, but based on literature, it looks more like myrtle than it does in candelilla. What's next? What do we do from here? So we have this information now. And one of the other things we do in our lab, aside from making devices, is we want to make new materials because we are material scientists and engineers. So we're using the material scientist part. We want to create new monomers. They'll generate new polymers. And then we can see, can these biodegrade back down? Or can we reuse them in some way after we don't need the device any longer? So that's the question. And so right now we've gotten as far as making the new monomers and we've made some polymers and we're right in the middle of doing some degradation studies. So alas, I cannot show you that today, but we're right in the middle of doing that. And once we get a handle on that, we're going to begin incorporating that into some flexible electronics as well. Another thing that you might already be thinking about is, gosh, this is a lot of devices. We're just going to be accessorizing from head to toe. We have to power these devices. How are we going to do that? And then piezoelectrics could be one way. If we could also make transient piezoelectric devices, then perhaps we could be using our own body to harvest the energy from our own body to power the devices that we'll be wearing, but then can degrade when we no longer need them. So it'd be a nice circular full life cycle design of electronics. So that's something I have just one slide of preliminary data on that, but want to share that with you as well. This is an example of our very first polymer that we made. It's just really short here. And so we combined these molecules together and made a polymer material. And we're excited for this, but if you're good in organic chemistry, you might note that that monomer may not be in the highest of yields, and that you have other byproducts as well. And so we are trying to figure out ways to improve that and also change the top group to other things to make the material properties either more sticky or more rigid, so we can try to control that. In the meantime, however, we're looking at two other monomers. These are known monomers. We didn't make these, but we were trying to think, what monomers should we use? Like, where do we start? And one of the reasons why we found bisphenol S and the fluorine 9 bisphenol of interest is because they're used everywhere, from food packaging to medical devices, filtration membranes, food storage. I think I already said food packaging, but they're everywhere. They're even sometimes found in paper receipts. And you might also know that bisphenol S and the BHPF are used as BPA replacements. We all hear about BPA. Even my bottle here says BPA free. There's no BPA in here. But the problem actually, and after we started doing this research, because we thought, okay, these are good alternatives, but it turns out that it's really the location, a big part of it, not all of it, but a part of it is the location of the hydroxyl groups. They're kind of locked in there on the aryl rings. And so even if you change the center structure, if you're looking at the hormone estradiol, that's the estrogen hormone, we know that if you have this endocrine disruption, it causes like neurological difficulties, developmental difficulties, obesity, diabetes. It's a really long list. Look at the structure for bisphenol S, for example. You see it overlaps with those oxygen groups, is right where those receptors are at. And that's a problem. And some other literature is now showing that even the fluorine derivative can fit into the estrogen-like receptors, and that's a problem too. So we thought two things. One, well, these are really important functional groups to use, but can we do two things? One, let's try to extend the hydroxyl group away so it doesn't exactly overlap anymore with those two hydroxyl groups. And then two, let's go ahead and make this biodegradable at the same time by using a step polymerization and then using hydrolysis. So not only should we make the diol version, but we should make the diacid version as well. And then we can put together different combinations of the diol with the diacid with either the fluorines or the sulfones, or vice versa. So let's see if they work in both ways. And then we wanted to just include some known monomers too. So the ones on the top is ethylene glycol, that's the reddish colored one. And then the 1,6-hexanediol is another known monomer diol. And so we wanted to see if we can control the glass transition temperature, right? This is the temperature at which it transitions from a glass to a rubber. And so we could modulate that and then compare the diol versus the diacid, that's these two together, and then same thing with the sulfone. And then we could do this with, just reverse that and use the sulfone instead of the fluorine and get some polymer materials as well. So we're, like I said, right in the middle of looking at the degradation studies for these. So I'm going to hold and until I finish that to share them with you. But one thing I liked, what was nice and convenient, is you can see that the trend for the glass transition temperature is similar for the different functional groups. So the ethylene glycol is higher, the hexane 1,6-diol is lower, the fluorine is higher, the sulfone is lower. But overall, when you use the sulfone version, you shift to a lower temperature. So those TGs are overall lower, even though they follow the same trend, or similar trend. And then when you look at the thermogravimetric analysis, they both can withstand up to very high temperatures, around 350, almost to 400 degrees, until they start losing 10% of their weight. That's kind of a standard measure. And it looks like a sulfone is much more stable because of this, change here, but I think statistically, really, they're quite similar. So I will just say that the fluorine derivatives have higher TG trends, but thermally, they're pretty similar in their stability. And this is step growth polymerization, so we expect to have, dispersity closer to 2, and some of the slower dispersity is not because I discovered something new. It's there's lower molecular weight materials. So if we do longer polymerizations, we'll definitely see that PDI increase. What's next for this then, as I kind of come into the home stretch, is one, okay, my hypothesis is that if we change the shape of it, we can still get useful properties, but that it won't cause endocrine disruption. And so we're right smack in the middle also of collaborating with a professor in the College of Medicine. It's next door to my research lab, so very convenient. This professor actually works in my same building, so really just down the hall. And so together we are culturing cells that have estrogen, activity or reception, and we're dosing it with our monomers versus controls, and also with BPA, so that we can compare in between. So I expect to have a result definitely before the end of the year, realistically. But I'd like to see something, coming out sometime in the month of September or October, where we can begin to write this part up. We're also, like I said, doing degradation 2 ways. One, we're going to use like UV in solution to see how maybe the UV absorption changes, and then also as thin films, because ultimately we want to put them into devices. And that's the ultimate thing we want to do. So the last thing, now I'm switching gears on you a little bit, but I warned you in advance, and that we want to look at piezoelectrics. How can we power these? And this is my last, data slide. But in this case, because we're developing new monomer here, why don't we look for a natural polymer over here? And we chose a branched polysaccharide. We did a branched polysaccharide because some polysaccharides, like chitin, for example, they can be really rigid and not like a little more hard. But if you branch, that's because they're linear polysaccharides. But if you branch it, then we have greater flexibility. And we also added a little bit of glycerin too to kind of make it a softer material. We made a polymer composite using barium titanate. Barium titanate is a piezoelectric nanoparticle or piezoelectric material, which you can make into a nanoparticle. And so the idea behind this is if you have an instrument or some method where you can put a reproducible force compression, then press, you're pressing it, it's pressed, you're releasing it, and then it's released, and you should be able to generate some voltage output. So this is just our very, very preliminary data. It's like brand new, where we look at 10%, for example, and 40%, and there's some variability. So we have some kinks to work out. I think some of that is coming from the fact that when we did our first SEM, you can see certainly there's some aggregation there, and that's something we're working out. So we're functionalizing these nanoparticles now to try to have better dispersion. We're thinking about adding a different type of additive to help that as well, and that should help to even out some of the differences that we see there. So of course, we want to make microfibers too. So if we can make microfibers and make composites of those, then we can have microfiber piezoelectric materials or semiconducting or conductive materials, where we're all studying the composite, the intermolecular interactions, but we can actually use them and incorporate them into devices too. And so this is a centrifugal force fitting instrument that was built entirely by undergraduates. So we're writing an instrument paper right now, and there will be no graduate students on this device. They did it all by themselves. And so now that we have the microfibers, we're beginning to make with different composites and use our own polymers too that are brand new, that haven't been made before. So that's something that is really exciting to me, because for one, yes, that's undergraduate education is important, graduate education is important, but really, something that is I think we all know is that a few moments, of attention can really fundamentally change a person's life trajectory. I think it's really amazing that we get to be a part of that. So this is something that's important to me. And one of the biggest honors I feel is that I had the opportunity recently at the University of Central Florida to chair the committee for developing a new undergraduate program. And so now UCF has a bachelor's degree in material science engineering. We had our first undergraduates graduate in May, and I'm just so honored to have been able to be such a big part of that development, because now in one academic year, we've already doubled our enrollment. We have at least 100 people that have noticed that they're interested in it. We have 60 people in the program, and this is just within a very short time frame. So being that we're the second university in Florida to have an MSc program, I'm just really excited to be part of that initiative. Then the take-home message. It's a story I told you today is that we want to live healthier, not just longer. There's no point living longer if we're not healthy. And we want to do this maybe using flexible electronics because it allows us to maintain, enhance, monitor, diagnose things much earlier. And that's part of maintaining our modern society. We don't want to move backwards in plastics. I didn't mention this, but the electronic waste, you're thinking electronics, but up to 90% of our electronics are composed of plastic. Take this keyboard, for example. There's a circuit, there's a board in here, but it's all plastic. You have silicone, some material here, and you have different types of plastic. And when this is done, what do we do with all this plastic? And so that's something to really keep in mind. How do we do that and maintain our society? We don't want to go backwards. We need these materials, but how can we do this in a more sustainable way? So the students that do the work are here. I would like to acknowledge them and also my mentors. I would not be here today without my mentors that played a really important part in my life. And I've listed the device collaborators. Those are individuals that led some of the projects that I talked about. So I would be very happy to answer any questions you guys have.
It's great talk, by the way. I'm also doing organic electro, but it's more like a energy storage and fundamental understanding. So it's always nice to see a device. So I believe it's on slide 11. You have maybe exposed energy to two different chemicals that change the color. I'm wondering how long you exposed.
That's a good question. That's been worked out now.
How it corresponding to, under the real sunlight.
Yeah. So I think that's a good question. In our paper, we focus primarily on very calculated amounts of UV exposure. And there was at the very end a device demonstration where one of us put it on and went for like a run outside. You could see it change colors. That might be in supporting information, so you see similar change. Now the time I didn't really think about it. I was thinking about the exposure level because you could be outside for a short period of time, but it's about how much exposure you're getting, what time of the day it is. So I did more of the energy exposure rather than.
Kaitlyn, can you repeat the question so that our Zoom audience can also hear it?
Oh, yes, sure. Thanks for reminding me of that. So this question was about with the UV dosimeter and how long it takes for like the color to change or how long it lasts for. And so my response, I think you probably heard. We have some
We're on mute.
Oh, were we on mute? No.
Oh, really?
We're good.
So you don't
I'm
give me
sorry.
a heart attack. Folks on Zoom, please type in the chat if you have questions.
Maybe type your
Tim,
question
can you
in the
type
chat.
your question? There's something probably wrong with our.
And it looks like you might have a question.
So I guess your attempt to power these devices, wearable devices using piezoelectric is very interesting. Have you also considered using thermoelectric materials in film?
Yeah, that's a really nice question. So the question was, if we're using piezoelectric materials, but have you considered using thermoelectric materials? So a lot of piezoelectric materials tend to have thermoelectric responses as well. And so I think it's a very interesting question because I was just talking to somebody at the ACS meeting about how we can figure out a collaboration because they look at thermoelectrics and they want to use some of my materials. And I want to see if their thermoelectrics will work in our materials. So we're going to switch and then you look at some of that more closely. But something like BTO also has some thermoelectric properties too. I was just focused on the piezoelectric. Nice.
It's easier to fabricate the thin film structures, and I think have more stable voltage current
Okay,
source, right?
yeah, sounds like we need to have a conversation about that. I would very happy to talk about it.
Caitlin?
Okay, there's a question here and then there's one in the audience. So let's take the ones on chat and then we'll go over here if that's okay.
So I think let's start with Tim's question and then move on to Christine.
The question, so you guys, in case you can't read it, is do the health monitoring devices that are being developed need to be sterilized prior to packaging and application? Yes. And typically ethylene oxide in water environments are used today. Yes, also true. So that's something that we have spent a bit of time on is especially with those optogenetic examples I showed very briefly on that slide, we had sterilized those. We actually used, there's another type of a liquid you can use. It's like a type of biocide. I'm forgetting the commercial name for it. So we dipped our devices in there because we were before using an autoclave. Like we wanted to see if our device could just survive the very standard autoclave, and they can like one time. And they're a little bit cloudy, so you can see they dry them really well afterward. But then when you try to use that autoclave more than once, then it's just too much for that to handle, just destroys it. And so then we would clean them with the solution that they used in their lab, which I can't remember the name of. So it wasn't ethylene oxide and water. No, it was more like, if anything, it was like IPA, but the medical version of that.
Thank you.
I'm sure, yeah. And then so thank you very much, Christina. What are you using the microfibers for? Oh, yes, great question. We could have like the next half an hour. I could talk about this. Like, I like shiny objects, like not because they're shiny, just like I like new things. So, like so many different things come to my mind. I have a new BME PhD student, and I think one of the very first things we're going to look at is making composites for antimicrobial. We want to make like a wound mesh and look at how we can use this bioresorbable wound mesh that's also antimicrobial and use that. So realistically, that's probably the first project we'll do because she will interface with the BME space in that way, and that's interesting to her. Oh, exciting. Okay, so we can also talk about that after the seminar too, if you're interested. So that's probably the first one. But I really would like to incorporate these with the piezoelectric, like barium titanate, or maybe the thermoelectric, excuse me. And then using, I have a collaborator in Israel. I recently came back from there in June, and I came back with some tungsten disulfide, and we want to see how this will mix in with our microfiber. So I have some semiconducting materials, and so yeah, gosh, like it's too many ideas to have the time to do. Thank you for that question.
Yeah, go ahead.
You talked about like monitoring thermal or I'm sorry, UV exposure and stuff like that on the surface of the skin. Would there be any like possible applications for monitoring something like airborne, like fine dust or like airborne, like harsh chemicals for someone in an industrial position, or is it focused more on like?
That's a great question. So the question was, we have the UV devices that look at, the UV exposure and the thermal properties of skin, but what about, like pollutants that you're breathing in that are in the air that you're exposed to in industrial or in everyday situations, depending on where you live? The answer is yes, people are looking at this. And so when I was collaborating on some of these projects, there were in parallel projects that were actually working on pollution when we had like a blender and like a dust buster, and we put the devices in the dust buster and see how much it could sense the dust that was in there or survive the fact that it's in the dust buster or a blender. We tried to like hang it from there, but I didn't do that personally. I just saw it around me. And so there are examples of those too. It's not something that I have worked on before.
Colin,
I have a small question based off of like the
louder.
I have a question regarding the design of the composite. So how are you guys fabricating the thin films with the piezoelectric fibers, and then what matrix do you select, and how do you guys actually like it's like a vacuum resin transfer or something? Like how are you making the film?
You want like this, like in the
Like
last,
the composite.
the composite, the one I just showed in the very last slide, like surprise, here's some more data for you. So that's a good question. The question is, how did we make the piezoelectric composite in that last slide? I like that you asked that because that one film took my graduate students like 6 months to make. And it was very difficult because at first they would crumble, we couldn't compress them, they wouldn't make films. We tried drop casting, but there were pinholes. It was like a lot of almost tears, but a lot of hard work too. So we finally figured out that if we make more of a paste, and that even though there was some aggregation here, we used a planetary mixer, which would really brought it to the next level using planetary mixing. So we're gonna keep that, but incorporate some other things too, like a sonication horn before we make it into a paste. And what we found is that if we use a paste material, and then we use a carver press, and we did thermal pressing, then that finally gave us really good films. But the key is how long you let it cool down, and then how long you let the water evaporate. Because if it goes too fast, and you end up with lots of wrinkles and some shrinkage, and that's if you also add too much water. So a very careful balance of water and letting it just dry very, very slowly. Then it's, you know, like after like 3 days, for example, it's slow drying, and then some heating, then we have really good, finally have really good films. We can do mechanical testing. That was another issue, by the way. So tangent question. These like dog bone cutouts for polymers, they're really difficult to come by. They're very expensive, or they're just difficult to find. So we use a CAD to make our own dog bone cutout, and then we had our machine shop make it. So finally, now that we have films, for time I cut it out, but we started doing mechanical measurements for our piezoelectric films too. And thank goodness we can make them. Great question. I'm happy to talk to you about it more if you're struggling making films, because it's not easy.
So I'm wondering if all these sensors, I mean, it's generic question, not a materials question, but all these sensors are not defeating the purpose about living healthy. And people are going to wear those sensors and thinking, oh, I'm doing something about my health, but they are going to continue eating meat, or they are going to continue drinking
That I
soda
agree.
and exposing themselves to the sun.
Yes, I love that. I like your provocative question. And I think it's something that should be talked about. So if you're on Zoom and you didn't hear it, it's that maybe we have all these beautiful devices and we're decorated from head to toe, but we just keep living, you know, like, it doesn't mean you're living healthier. It just means you have more data. You have more data about what happens when you eat that sugar donut. Doesn't mean you're not going to eat it. And you have more data about the fact that you're sunburned. It doesn't mean you're not going to walk outside. So I think those are really important questions to address, and it needs to be done in like a, you know, like really need to change the way that we think about the things that we're eating. We are machines, right? We're machines. And then you wouldn't go to a normal car and put in diesel, you know, fuel. That doesn't make sense. So why do we eat things like donuts when it's just not the fuel for this machine? And that's like a whole mentality. That's a dangerous conversation, but that's important. But what is also dangerous about this, and why I said it was provocative, is that then they have this ethical issue. Do you want that data collected about you? Do you want your insurance company to know that you ate that donut when you know you were not supposed to eat that donut? I don't want it. So then you have a compliance issue. And this is something that we discussed when we had a thought meeting with the Air Force. We were trying to figure out what is the next direction. And so it was a great group of people. We had psychologists and engineers and chemists and actual like fighter pilots in the room. So we had everybody. And the big issue is the compliance. Like if I'm stressed out, I don't necessarily want my employer to know that I'm stressed out so that you wouldn't wear the device. So that's a good question. Yeah.
Any questions from the Zoom audience? Oh. You want to read this question?
Oh, great. That's nice. Really enjoyed. Thank you, Tim. What is the current state of the art for synthetic skin model? Oh, wrong question. Wrong.
No, there are two questions.
Oh.
Let's ask. Why don't you answer Tim's and then we can move on.
Okay, okay, thank you. Considering the complexity and variability of what is the current state of the art for synthetic skin models? Yeah, because skin is complex. And how can we measure or model transport across skin in a laboratory model to accelerate the discovery? Yeah, Professor Long, you it's a thoughtful question. So we ended up using different types of silicones that we would make as composites. So if we wanted to have a slightly higher thermal conductivity, then we would add particles that were higher thermal conductivity, made a composite, we'd measure that, and then we use our device to measure it. And we made them in different thicknesses, and we would use a UVO exposure to laminate our silicones together, so they would become like one layer when you have multiple layers of different thermal conductivity. That's what we used. And before I went into using that, we made like small punch outs of like small petri dishes. Before that though, I spent a long time trying to find synthetic skins, and agarose is a very common synthetic skin when you're trying to with a high water content, but that's not what we were going for. So silicones work for us, but yeah, we need to figure out better ways. I think if we really want to make synthetic skin, then we need to mimic something more like a skin graft. So that's one other thing that is not, I didn't share with you today, but for a minute there, we actually got skin graft from the clinical side, and we had skin grafts in the lab. It's just those are very expensive. So after we used it once, then we didn't get any more because they're too costly. And so I don't have a good answer for how to accelerate it right now. But I think
Yeah. Thank you, Kaitlyn. Excellent.
excellent. Okay, so Mark asked in your talk about how to use biodegradable hydrophobic materials derived from soybeans, etc., to develop the encapsulant for water-sensitive biomaterials. Okay, can you explain a process of how you develop such hydrophobic coatings from soybeans? No, I just had the wax. I bought the wax from Amazon. No, do not have a good answer for you there.
Sorry, Mark.
Yeah, sorry. And Marat also, thank you, Marat. A comment, not a question. Heat stress measurements on skin are also relevant for people and protective equipment working with molten metals and alloys. Yes, so new markets. Yeah, it's a hot environment as well. Thank you for that. I did not say that in my talk.
Any other questions? I'm always embarrassed to ask this question. Tim asked the question much better, but when you're measuring the extent of thermal conductivity as a function of sunburn and stuff, I mean, you do take into again going back to the complexity and the variability of skin, right? I mean, thick hair.
Yeah, hair was a problem, so we just shaved the hair.
Yeah.
If we needed, if it was too long or it wasn't fine enough.
But what if it's sunburned? Could you still shave that?
Of course you could. I mean, maybe you should stay out of the sun, really. One thing that you just did remind me of that I didn't share that I think is really important is you might also be thinking why we wear, like, I can see the sunburn. Like, what's the big deal? The big deal is that I have fair skin. I have Fitzpatrick type 1 skin. I always burn. I never tan. But we have all the way to Fitzpatrick type 6, which is the darkest, blackest skin. And somewhere in there, you don't see sunburn anymore. And so even though fair-skinned individuals with Fitzpatrick type 1 skin are diagnosed with skin cancer more often, African Americans die from skin cancer more often because we just don't see the sunburn. It goes neglected, and then skin cancer develops. So that is a motivation thing that I missed in including. You had a question, if we have time.
So I think it's let's.
Can I go just really quickly? So I know the whole notion is preventative. What if someone's already using UV sunscreens and stuff? Would it interact with the device?
In the UV dosimeter?
Yeah, like
We already applied a sunscreen on our skin.
was that?
So what we did is, that's a great question. It's about, what about the UV dosimeter and the, if you're already wearing sunscreen. So we just put the sunscreen right over the UV dosimeter. And that way it had a coating of sunscreen on it too.
The doctor sometimes the effect of the sunscreen is reduced, right?
Yes, and then,
Suppose it's for 2 hours.
Yeah.
And after that, you need to reapply that.
yeah, you'll need to you have to reapply the sunscreen. So we reapply it to the device as well. Otherwise you'll see it start to change color. And when you do put sunscreen over it, it does take a lot longer for the color to change. Yeah, great question.
I think we need to call it a day, at least from the seminar point of view. Thanks a lot, Kaitlyn, for a great seminar. I need to add that we've had these seminars for 2 years, and I think barring one, this is this is the first time actually that the UFA that we are having the in-person seminar in the last 2 years. So thanks a lot for coming, and This is great. I think last year ASU had one in person. But other than that, it's we are moving away more and more from Zoom days.
Yeah, onward and upward.
Yeah.
Back to people.
Thank you.
Nice to see you all.
Thank you so much.
Yeah, great questions today.